Average rates of change, part 3. You should remember that the average rate of change is a change in your output variable divided by your change in your input variable. And that is your average rate of change. Today we're going to analyze what happens to the average rate of change at different parts of our line or our curves down here. So our first example is a linear function. It's called linear because it's a line. It's because it's straight. Now, if I were to calculate the average rate of change here, right, it moves forward by 1, and it's going up not by 3, but by 30. It's adding 30, right? And then if I move forward here by 1, it goes up by 30 over here as well. If I move forward by 1 here, it's going up by 30. No matter where I'm at, if I move forward by 1, it's always going up by 30. No matter where I'm at on the curve or the line. Plus 1, plus 30. Plus 1, plus 30. So for a linear function, the average rate of change is always constant. This means that if you pick any 2 points and calculate the average rate of change in that area, you will get the same rate every time. And even if you pick the first point and the last point and you calculate the average rate of change, it's going to be the same number. So that's the point. Linear functions have a constant rate of change. Another way of looking at that is what's called a first difference. A first difference is when I find how I get from this y value to that y value. And a first difference only works as long as my table is evenly spaced. So to get from negative 40 to negative 10, I added 30. To get from negative 10 to 20, I added 30. To get from 20 to 50, I added 30. No matter what happens, I get the same number. It's evenly spaced. My first difference is constant. So a linear function has a constant average rate of change. It also has a constant first difference. Our next function we're going to talk about is a quadratic function. A quadratic function is some sort of function that has x squared in its term. Okay? Somewhere in the formula there's going to be an x squared. We have concave up is a cup. So if you ever see a curve that looks very happy, it's a cup. That's called concave up. And concave down is a frown, right? Frown is an English word that describes the way your face looks when you're not happy. And it's actually going to be quite interesting to note that there's going to be something positive about this and something negative about that. But what exactly is positive and negative? So let's first fill out our tables with the data points. So what happens when I pick these 2 points to figure out the average rate of change? It's going down and across, right? So this secant line right here is going to have a negative average rate of change. And if I calculate it, it's going to be negative 3.5. And how do I know that? It dropped from 8 to 4.5, which is a drop of negative 3.5, and I'm dividing that by 1. But from here to here, it's not dropping as much. Going from 4.5 to 2, that's a drop of 2.5. And going from here to here is a drop of negative 1.5. As I move forward, it's dropping less. It drops the least amount when I get close to the minimum here. It drops by negative 0.5. And then it starts to rise. It starts to go up by 0.5. And then it goes up by 1.5. And then it goes up by 2.5. And finally, it goes up by 3.5. It's symmetrical. And you're going to notice that I just actually, even though I did the first difference, this is also the average rates of changes in those particular segments because I'm dividing by 1 every time. If I look at the change in x in all of these secant lines, I'm always adding 1, right? And to divide by 1 is not to change a number. So a concave up curve does not have a constant average rate of change. It has a changing average rate of change. A linear function has a constant rate of change. A quadratic function, or a curve, has a changing rate of change. And therefore, if my concave up curve, you're going to notice my average rate of change is getting larger and larger. It's increasing. It's adding 1 every time. That means my average rate of change is changing plus 1 itself. Now, when I'm finding the difference of a difference, that's called a second difference. So concave up curves have a increasing average rate of change, and they're going to have a constant positive second difference. And in this case, it was plus 1. If my second difference is a constant number, I know that I'm going to have a second power in my polynomial. Let's take a look at the concave down as a frown. First of all, we're going to plug in the data points to the table. Well, the first thing I'm going to ask you to notice is that my x values are still evenly spaced, but the spacing between them is now 5. So I could calculate the average rates of change for all of these secant lines, but that's going to require some division that I don't want to do. I kind of want to get a point across. So I'm just going to focus on the first difference. And first differences only mean things as long as our table is evenly spaced. So to get from negative 125 to 0, I have to add 125. And to get from 0 to 75, I have to add 75. And then I'm adding 25. And then to get from 100 to 75, I am dropping by 25. And then I'm dropping by negative 75. So over here, my average rates of changes were positive because I'm increasing. I get to my maximum, and my average rates of changes are going to start to become negative because I'm now going in the opposite direction. So look, my average rates of change, they're not constant. I mean, in a linear function, the average rates of changes are a constant number. But here, they're dropping. They're decreasing. A concave down curve has a decreasing rate of change. And watch this. If I find a second difference between these numbers, notice, to get from 125 to 75, I'm dropping by 50. To get from 75 to 25, I'm dropping 50. And then that's a drop of 50. And then that's a drop of 50. You're going to notice my second difference is also a constant, but it's a negative second difference. So in summary, linear functions have a constant average rate of change, or also they have a constant first difference. Quadratic functions have constant second differences. If my second difference is positive, I'm going to get a concave up curve. It means that I have an increasing average rate of change. If my second difference is negative, it means I'm going to have a concave down curve, because that would mean my average rates of changes were decreasing the entire time. So in summary, constant average rate of change means it's linear. It doesn't matter if it's going up or down. The average rates of changes are constant on those lines. An increasing average rate of change means I have a curve that's concave up. And a decreasing average rate of change means I have a curve that is concave down.